In this video, our objectives are to solve two different types of inequalities. One type is polynomial inequalities, and the other is rational inequalities. And we want to try to solve them two ways, both algebraically, without using a graph, and graphically. We've recently talked about how to graph polynomial functions and rational functions, so that information will be used again here when we try to solve the inequalities graphically. So first, let's go through the list of how to solve a polynomial inequality algebraically without a graph. The first step is to get a 0 on one side and solve the related equation by factoring. Once we have solved the related equation by factoring, we'll use our solutions and put them on a number line, which will divide our number line into several intervals. From each of those intervals, we'll choose a test point that's not an endpoint. We'll substitute that value into our original inequality or into the inequality arranged to get a 0 on one side, and we'll determine whether we get a true or a false statement on each interval. Those intervals where we get a true statement will form our solution set. So our solution set is going to be a set of intervals, and we'll use the chart and the test points we've found from the first three steps to determine the solution set. Before we talk about how to solve these graphically, let's go through our first example just algebraically. So over here I'll have our algebraic solution. Our first inequality is x minus 3 squared times x plus 2 is greater than 0. So what we want to do is first solve the related equation. And that equation would be x minus 3 squared times x plus 2 equals 0. And then the nice thing is that this is a factored expression on the left side equal to 0, so we can just set each factor to 0. So we solve each equation here. X minus 3 squared equals 0. You don't want to do x equals 3 or x equals negative 3. Instead, we take the positive or negative square root of 0, so we'd have x minus 3 equals positive or negative square root of 0. So that's just x minus 3 equals 0. So just x equals 3 is our only solution. So be careful of that as a frequent error that I see, to take positive and negative 3 instead of the positive and negative 0. And then on the other equation, we just get x equals negative 2. So we have two numbers to put on our number line. And make sure you put them on in the correct order. So we want to have negative 2 to the left of 3. And here what we can do is say I'm going to have three intervals, A, B, C. And the first interval is going to be from negative infinity to negative 2, and I need to choose whether I want to put square brackets or parentheses around the end of that interval. Because it's greater than without the equal to symbol, I'm going to do parentheses. And then interval B is from negative 2 to 3, again parentheses because there's not an equal to, and then 3 to infinity for interval C. Then what I need to do is test some value from each interval in my inequality. So what I want to do is test x minus 3 squared times x plus 2 greater than 0 on each interval. So I'm going to make a little chart. A, B, C, my test point, my test, which I'll write again. And what I want to do is pick a specific test point. So in interval A, I'll take, I don't know, something less than -2, so I'll just take -3. In interval B, I want something between -2 and 3, I'll take 0. Interval C, I want something larger than 3, so I'll just take 4. But I could take anything in the interval as long as it's not an endpoint. And then I'm going to put this x value in and check how what becomes of this expression. X minus 3 would be -3 minus 3, so -6 squared. X plus 2 would be -3 plus 2, so -1. And overall, this is negative because I've got 3 negative factors. So -6 squared would be +36 times -1, that's going to be negative. Notice that I don't really care what the value is, I just care is it positive or negative. So rather than checking the actual value, I'm going to just test the sign of each factor. So when I substitute x equals 0, I would have 0 minus 3 squared, so that's a negative squared times 0 plus 2 times a positive. So that's going to be positive overall. When I put 4 in, I would have 4 minus 3, so that's a +1 squared times 4 plus 2, that's positive. So overall I have positive for the sign on that interval as well. So if I'm looking for where this is greater than 0, it's not greater than 0 on the first interval. It is greater than 0 on the last 2 intervals. So my solution set, which I'll go back up here and write, because I was looking for greater than 0, I'm choosing the intervals where my factors gave me a positive product, and then I wrote true for those 2 intervals, so interval A and B and C. So the solutions should be -2 to 3 union 3 to infinity. Notice I don't want to include 3, so I can't just say -2 to infinity, because at 3 I have equality with 0 instead of greater than 0. So my solution is exactly these 2 intervals, and I cannot combine them into one. Now let's take a look at this graphically. So if I scroll back a little bit, to solve an inequality graphically, it helps to remember that when we're looking for a function greater than 0 or a function greater than or equal to 0, we're looking for where the y values are above 0, which would mean above the x-axis. If we have f of x less than 0 or f of x less than or equal to 0, we're looking for where the y values are below the x-axis or below or touching the x-axis. So what we're looking for are the intervals of x values over which the points are above the x-axis or below the x-axis, or again touching if we're talking about x equals 0, or f of x equals 0. To solve those inequalities, we first have to figure out where the graph touches the x-axis, or possibly where the function is undefined in the case of rational expressions. And then using those places where the graph touches the x-axis or is undefined, we'll figure out where the graph is below or above the x-axis on the intervals between those x-intercepts or vertical asymptotes. So the key is to first find the x-intercepts and vertical asymptotes, if there are any, and then search between those points for the sign of the expression. So here I want to graph f of x equals x minus 3 squared times x plus 2. Find the x-intercepts. And then determine where the graph is above the x-axis, because we want it greater than or equal to 0. So graph the function, find the x-intercepts, determine the x-intervals over which the graph is above the x-axis. So, thinking about this function, our x-intercepts would be 3, 0, and negative 2, 0, since we have factored form. 3, 0 is multiplicity 2, and negative 2, 0 is going to have multiplicity 1. So we're going to touch but not cross the axis on the first one, and cross the axis on the second one. Except the first one we cross is actually negative 2, and then the second one we get to is 3. So, end behavior, this is degree 3 with a positive lead coefficient. So the end behavior is going to look like that. Great. So when we get to negative 2 and 3, we want to be careful about what's going on. We're going to be coming up from down here. When we get to negative 2, we cross. Get to 3, we bounce or touch the axis and turn around. And the graph should look like that. So the intervals over which the graph is above the x-axis are that interval and that interval, exactly what we found in the previous example. So our solution set would be from negative 2 to 3, union with the interval from 3 to infinity, because we know this graph isn't going to turn around anywhere else. We, again, don't want to include either the negative 2 or 3, because at that point the graph is touching the axis, which means the function would be equal to 0, and we want greater than 0, not equal to 0. So it seems like the graphical solution is probably a faster way to get to the answer. It's important to be able to take both approaches. Moving on to example 2, or letter B here. Again, we'll first let's do an algebraic solution. And we want to solve the related equation. which means we want to look at x cubed plus x squared equals 6x. We want to get a 0 on one side. And then we want to factor it. We can take an x out for the greatest common factor. And we use reverse FOIL here. We have x plus 3x minus 2. So we can see our solutions are 0, -3, and 2. Then we create a number line. With those values in the correct order. So we want -3, and then 0, and then 2, which gives us now 4 intervals. If I write each interval underneath, I would have -infinity to -3. This time I'm going to choose a square bracket because there is an equal to symbol with my inequality. And -3 to 0. Again, square brackets because of the equal to symbol. 0 to 2, and then 2 to infinity. So 4 intervals. And then we do our test. And this time I'm just going to say I'm testing. I'm going to rearrange this into the factored form. So I'm going to have x plus 3 times x minus 2 less than or equal to 0. Because if I rearrange my inequality, I would subtract 6x from both sides. I'd have less than or equal to 0, and I can factor the other side. So this is what I want to test. And it's always nicer to test the factored form of the inequality instead of the original form. So if I want to pick a specific test point, I can. But really, it's just fine to think about any general value in that interval. We'll write a test point down in case you want to work through the specific value. But we really are worried about the sign of x times x plus 3 times x minus 2. So let's keep track of a little less than we did on our previous chart. So interval A, if I want to pick a value, something like -4, -5, anything less than -3. Even though -3 is included in our solution set, we don't want to use it as a test point because on the endpoints we get 0, which is not a signed value. So let's take -4 in interval A, maybe -2 in interval B, 1 in interval C, and 3 in interval D. Something larger than 2 in interval D, something between 0 and 2 in interval C, and so on. And then I'm just thinking about the sign of each factor. X is going to be negative. X plus 3 is also negative. X minus 2 is also negative. So we have a negative times a negative times a negative, which is negative overall. And if x is -2 or any other value in interval B, x itself is negative, but now x plus 3 is positive, and x minus 2 would be negative. So we've got a negative factor times a positive factor times a negative factor, which means a positive overall because we have 2 negative factors only. Now when we move on to interval C and pick a test point like x equals 1, x will be positive, x plus 3 will still be positive, x minus 2 though is negative. A product of 2 positive and 1 negative factors is negative. And then interval D, if we pick a value like 3 or anything else in interval D, x plus 3, and x minus 2 will all be positive. So we'll have 3 positive factors which will yield a positive product. Then we look back and we wanted to know where this product was less than or equal to 0. So we can see we want intervals A and C. So A was negative infinity to negative 3, and C was 0 to 2. Let's also take a look at a graphical solution. For the graphical solution, we want to graph f of x equals, in this case, x times x plus 3 times x minus 2. We want to look at the function we have once we had 0 on one side of the inequality. So we're thinking about x cubed plus x squared minus 6x less than or equal to 0. We're thinking about that equivalent inequality. So graph that function, find the x-intercepts, determine where the graph is, this case, below or touching the x-axis. So the x-intercepts, because this is factored, we can see are going to be 0, 0, negative 3, 0, 2, 0, each multiplicity 1. So at each point we're going to cross the x-axis. The end behavior is just like the last one, positive degree 3, so we know the end behavior is like that. And that's enough to pull our graph together. So we don't need a detailed sketch, we just need to know what's the end behavior and where are the x-intercepts, are we crossing or turning around at each x-intercept. So coming up from the left side below the x-axis, we're going to cross at negative 3. Coming back down, we cross at 0, and then going back up, we cross at 2. So again, we were choosing below or touching the x-axis because of the less than or equal to 0. Looks like the first interval and then the third interval we would have the graph below or touching the x-axis. So our solution set is going to be negative infinity to negative 3, union 0 to 2. And again, we're including square brackets, or using square brackets to include the endpoints because of the equality in the inequality, so less than or equal to 0. So again, back to that algebraic solution, what we're really worried about is just the sign of the expression, and that can be determined by the sign of each factor and then thinking about how the factors work together. So choosing a specific test point is fine, or if you just want to think, if I have anything in interval A, what's the sign of x going to be? Anything in interval A, what's the sign of x plus 3 going to be? Anything in interval A, what's the sign of x minus 2 going to be? And then also notice, if you're also thinking about multiplicities of each factor, any factor that's multiplicity 1, when you cross the value connected with that factor, the sign for that factor is going to change. So notice when we moved from interval A to interval B, the sign of x plus 3 switched. That was our middle factor. It switched from positive to negative. When we moved from interval B to interval C, when we crossed 0, the sign of x changed, right? We moved, the first factor switched from negative to positive. And then finally, when we moved from interval C to D, the sign of x minus 2 changed from negative to positive. So a lot of what we know about the graph can inform what we're doing here on our sign chart as well. Now we're going to take a look at solving rational inequalities, and again, we'll solve them both algebraically and graphically. And the process is going to be much the same as it was in solving polynomial inequalities. The only difference is that we not only have to keep track of the x-intercepts, the places where the graph is equal to 0 or the expression is equal to 0, we also need to pay attention to places where the graph is undefined or where the function is undefined, because that would mean we are thinking graphically about a vertical asymptote, and we know the sign can switch on either side of a vertical asymptote. So our steps are write the inequality so that we have a rational expression is on the left side and 0 is on the right side. We want the rational expression written as a single quotient rather than as a sum of two different terms. Solve the related equation, and also, this is what's new, determine any values for which the function is undefined, which would be zeros of the denominator. Solving the related equation is always going to be finding the zeros of the numerator, and we'll see why in a minute. Then we do just what we did in the other, divide the number line into intervals, but this time we include both the zeros of the denominator and the solutions to the original equation. And then we choose a test point from each interval, figure out whether the test point gives us a positive or negative value, and then write our solution set in interval form. The thing we need to be careful of is we never include any values that make the denominator 0, because at those points we would have an undefined expression rather than something that's positive or negative or 0. So let's go through a couple of examples here. So if I'm going to solve this rational inequality, first thing I want to do is rewrite. I want to take this and make it y, or 4 over y plus 2 is less than 0. And then I want to get a common denominator. So I'm going to take 4 over y plus 2 times y plus 2 over y plus 2 to get that same denominator. Multiply by a form of 1. So that's going to give me 4 plus 2y plus 4. So 8 plus 2y over y plus 2 is less than 0. And that's the inequality I want to work with. So the related equation would be 8 plus 2y over y plus 2 equals 0. So if I multiply on both sides by y plus 2 to clear out the fraction, I'm just going to have 8 plus 2y equals 0. And then if I solve that, I'll have 2y equals negative 8 y equals negative 4. And we want to make sure we realize that y cannot be negative 2. Excuse me, because that would make the expression undefined. So the solution to the equation is y equals negative 4, and the place where this function would be undefined would be y equals negative 2. So we do a number line. Put the values on in the correct order, so negative 4 and then negative 2. I put a circle around negative 2 because I like to remember that that cannot be included. I have A, B, and C for my intervals. I'm going to write each interval underneath, negative infinity to negative 4. And I want to choose parentheses because there was not an equal to symbol in my original equation, or my original inequality. Then interval B would be negative 4 to negative 2, parentheses again. Even if there had been an equal to symbol on this one, I would want to have parentheses around negative 2 because it cannot be included. It makes the expression undefined. And then C would be negative 2 to infinity. And then I want to do my test. And this time I'm wanting to check the sign of eight plus 2y over y plus 2. If I want to make that 8 plus 2y 2 times y plus 4, I could do that, but this is fine. Interval A, I'll take maybe negative 5 to be thinking about. Interval B, I'll take negative 3. Interval C, I'll take 0. Anything in the interval you can use in your mind. 8 plus 2 times negative 5, that's going to be negative. And the denominator, negative 5 plus 2, that's also negative. Negative over negative is going to yield a positive quotient. And then moving on to negative 3, 8 plus 2 times negative 3, that's 8 plus 2 times, or 8 plus negative 6, so that's positive. In the numerator, and the denominator is negative. A positive divided by a negative is negative. And then if I have 0 for my y value, I have a positive numerator and a positive denominator. And quotient of two positive values is positive. And then I go back and I look, I wanted to know where the expression was less than 0, so I would take interval B where the factors gave me a negative quotient. So the solution here is just the interval from negative 4 to negative 2. So taking a look at the graphical solution now, I will use this rearranged form of the inequality, and actually I'll factor that numerator too. Could have done that before. So I'm looking at 2 times the quantity y plus 4 over y plus 2 is less than or equal to is less than 0. So I want to graph. I could say f of x equals 2 x plus 4 over x plus 2. And then find the x-intercepts and the vertical asymptotes, and then use the graph and those pieces to determine the x intervals over which the graph is below the x-axis, because it was less than 0 that we're looking for. So less than 0 means below the x-axis. We can see, because this is in factored form, that the x-intercept would be the 0 of the numerator, so -4, 0. And the vertical asymptote would be at x equals -2. Both are multiplicity 1. So at each one, we're going to change signs for the function. So here's our -4, 0, and then x equals -2. We've got an asymptote. We can also see that, let's see, we need a place to get started with our points, something that's not on the x-axis. If we plug in x equals 0, say, we'll have 8 over 2, which means we'll have a positive value. +4. We don't really care that it's 4, but then we know that the graph is going to not cross the x-axis as it moves toward this vertical asymptote, so it's got to go up. And on the other side, because this vertical asymptote is odd multiplicity, we're going to be switching signs. So one side is up, the other side down. And then we cross this x-intercept, and we don't have a place to cross again. We can also see there's going to be a horizontal asymptote at y equals 2. It's going to look a little slanty here, but the graph should look like that. So the interval over which it's below the x-axis appears to be right in here. So our solution is just what we found in the algebraic solution, -4 to -2, not including either endpoint. Just one other side note here. If the inequality had been instead 8 plus 2y over y plus 2 greater than or equal to 0, notice that we don't need to do any more work to solve that. We would do the same amount of work in the same process, but then we would just take different information from our chart. So then we'd want the positive intervals, so interval A, but we would include a square bracket on the -4, because that was a place where the original inequality was equal to 0. And then we'd also want interval C, because that was a positive interval. But on interval C, we would not include -2, because at that point the expression is undefined, not equal to 0. And from the graph, we see that same thing. We want to figure out where the graph is above or touching the x-axis. So the first interval from -∞ to -4, including -4, because we're touching the x-axis there. And then the interval from -2 to infinity, over that interval, we're above the x-axis. Okay, then looking at example B here, again, we'll look at both an algebraic and a graphical solution. This time the inequality is already in the form we want, where we have a single rational expression on the left side and a 0 on the other side. So we'll skip right to the related equation. The solution, if we multiply both sides by x, we'll just have 2x minus 3 squared equals 0. So we take the positive or negative square root of 0, that just gives us 0. So the only possibility is that 2x minus 3 is 0, which means x is 3 halves, or 1.5. And we want to also notice that x cannot be 0 because of the 0 in the denominator. So switching to our number line, the values we want to include are 0 and 1.5. So we've got 3 intervals, A, B, and C. Again, I would put some indication on my number line that 0 can't be included no matter what. And then interval A would be negative infinity to 0, not including 0, even if there had been an equality with that inequality. And then 0 to 1.5. 1.5 not included because there was not an equal sign. 0 not included because it makes this 0 in the denominator. And then finally interval C, 1.5 to infinity. And then we want to make our chart and test the sign of 2x minus 3 squared over x. So choose a test value if you want, or I guess I'm calling that a test point. Or you can just think about anything in the interval, what the sign of each factor is going to be. So we want to test the sign of 2x minus 3 squared over x. Notice the numerator is always going to be positive because it's squared, right? Choose a test point. I'll take negative 1 in interval A, 1 in interval B, and 2 in interval C. The sign of the numerator is going to always be positive. Officially, this would be a negative squared over a negative. And then when I put in 1, I have 2 minus 3, so that's still negative, but we're squaring it. Now the denominator is positive. When I have x equals 2, the numerator is now a positive squared, and the denominator is positive. So the first one, our quotient will be negative. The second one, our quotient is positive, and the last one, our quotient is positive. And we were looking for where this is greater than 0. So we choose positive intervals, which were B and C. So our solution, we want interval B, which was 0 to 1.5, together with interval C, which was 1.5 to infinity. We don't want to include 1.5 because we didn't want equal to 0. And at the value 1.5, the expression is equal to 0, not just greater than 0. So 2 separate intervals, 0 to 1.5, union 1.5 to infinity. Then the graphical solution. We want to sketch the graph of f of x equals 2x minus 3 squared over x. And we'll use the x-intercepts and the vertical asymptotes to determine where, talking about x intervals, the graph is above the x-axis because we want it greater than 0. So the x-intercepts, zeros of the numerator, which would be 1.5, 0, multiplicity 2, and the vertical asymptote would be at x equals 0, and that's multiplicity 1. So an x-intercept at 1.5, a vertical asymptote on the y-axis, if I substitute a value like, I don't know, x equals 1, I have 2 times 1 minus 3 squared over 1. So that's a positive value, right? So I know at x equals 1, my y value is positive. I know then as I move closer to this vertical asymptote, I have to go up because there's nowhere to cross the x-axis between 1 and 0. Because that vertical asymptote is multiplicity 1, on the other side I know I have to be down. And I also know because I'm not crossing the x-axis that I have to stay negative to the left of the y-axis. As I move closer to this x-intercept, because it's multiplicity 2, I'm going to need to turn around and then go back up. So if I want to know where the graph is above the x-axis, not touching the x-axis, I can see I want the interval from 0 to 1.5 and then 1.5 to infinity. Just like we had from our algebraic solution. So again, everything needs to fit together. Helps to have two approaches. Another rational inequality here with just a lot more factors, a lot more going on. So first we're going to look at an algebraic solution. Again, this is nice because it's all in the form we wanted already. It's factored on the left side, a single rational expression, and a 0 on the right side. So we'd have first our related equation, which would be x minus 2 times x plus 2 over x plus 1 squared times x minus 4, and we want to know where that's equal to 0. And again, we would clear out the fraction by multiplying by the denominator, which is just going to give us x plus 2 times x minus 2 equals 0. I changed the order there, but that doesn't matter. So we'll get x equals negative 2 and x equals 2 as our two solutions to the related equation. But we don't want the denominator to be 0. Which means x plus 1 can't be 0, and x minus 4 can't be 0. So x is not negative 1, and x is not 4. Remember, for this squared factor, that's just really x plus 1 2 times. So there's not an x minus 1 in the mix. So we don't want x is positive or negative 1. We just want x can't be negative 1, because that would make the denominator 0. So we put 4 values on our number line, and 2 of them we want to avoid in our solution set because we don't want to include them since they make the denominator 0. So our number line, we want to put the values -2, -1, 2, and 4, and we want to pay close attention to 4 and -1 because they're zeros of the denominator. So this time we actually have 5 intervals, A, B, C, D, and E. There's always one more interval than solutions to your equation or vertical asymptotes. So let's see. A is going to be -infinity to -2. We choose to include brackets on -2 because it's not a zero of the denominator and because there was an equality together with the less than there. B, we would take -2 to -1, but -1 will not be included, so parentheses around that, since that's a zero of the denominator. C would be -1 to 2, include brackets on the 2. D would be 2 to 4, again 2 included because of the equal to symbol, 4 excluded because it makes a zero in the denominator, and then E would be 4 to infinity. And then we want to test the sign of x minus 2 times x plus 2 over x plus 1 squared times x minus 4. So 4 factors to keep track of and 5 intervals. A test point, if I want an interval A, maybe I'll take -3. Interval B, I don't have an integer value to take, but I could take like -1.5. Interval C, I'll take 0. D, I'll take 3. And then E, I'll take 5. Then I just want to think about the sign of each of these factors. X minus 2 is going to be negative if x is -3. X plus 2 is also negative. X plus 1 squared is a negative squared. X minus 4 is negative. So the square factor will be positive. I have 3 negative factors, so a negative quotient overall. If x is -1.5, x minus 2 is still negative, but now x plus 2 is positive. X plus 1 would be negative, but I'm squaring it. X minus 4 is negative. Again, the square factor is going to be positive. I have 2 other negative factors, so positive quotient. When x is 0, I would have a negative for x minus 2, positive for x plus 2, positive squared from x plus 1 squared, and a negative. So I have 2 negative factors, so my product will be, my quotient will be positive. Using x equals 3 or anything else in interval D, x minus 2 would be positive this time. X plus 2 is positive, x plus 1 squared would be positive and then squared. But that last factor, x minus 4, will still be negative. So my quotient will be negative. And then when I get to 5 or anything else in interval E, each factor will be positive. So the quotient is positive. Then we look back to what we were looking for. We wanted to know where this expression was less than or equal to 0. So we want the places where the quotient was negative. Looks like interval A, interval D. So the solution set is -infinity to -2 including negative 2, union 2 to 4, including 2 but not including 4. And then finally, let's look at this graphically. We want to look at the graph of f of x equals x minus 2 times x plus 2 over x plus 1 squared times x minus 4. This graph has x-intercepts at 2, 0 and negative 2, 0. Has vertical asymptotes at x equals negative 1 and x equals 4. Both x-intercepts are multiplicity 1, but the vertical asymptote at x equals negative 1 is multiplicity 2, and at x equals 4, multiplicity 1. It will probably help us to think about the horizontal asymptote as well. The degree of the denominator is larger than the degree of the numerator, so there's a horizontal asymptote at y equals 0. And we'll need a point that's not on the x-axis to get started. This time, if we plug in f of 0, that's not going to be 0. It would have negative 2 times 2 over 1 times negative 4, which is negative 1. Nope, positive 1. It's important to get the sign right. That's what we really care about. So negative 4 over negative 4, that's positive 1. Then we should be able to put a graph together. So x-intercepts at 2 and negative 2, vertical asymptotes at negative 1 and 4. F of 0 is 1, and there's a horizontal asymptote on the x-axis. So moving from this y-intercept, if I go to the left, I have to go up because I don't have a place to cross the x-axis. That vertical asymptote at negative 1 was multiplicity 2, so it's going to be the same on the other side. We cross that x-intercept and then go up because of the horizontal asymptote at y equals 0. We get to the other x-intercept, we cross because that was multiplicity 1. We get to the vertical asymptote. On the other side, it's got to be the other direction because this is also multiplicity 1. So there's our graph. And we wanted to know where the expression was less than or equal to 0. So where is the graph touching or below the x-axis? It looks like on this stretch and this stretch. So our solution set would be negative infinity to negative 2, including negative 2 because they were touching the x-axis, and then 2 to 4, including 2 because we're touching the x-axis, but not including 4 because that's a vertical asymptote. And again, that matches exactly what we found from our algebraic solution. The last couple examples here are, one is just an application of this where we're going to need to solve a rational inequality or a polynomial inequality, and then the other one is just looking at solving these using our graphing calculators. So the last example here with talking about domains. So if we have a square root function, keep in mind that whatever's inside that square root needs to be positive. So if I want to find the domain of this function, f of x equals square root of x plus 3 over 2 minus x, I need to solve x plus 3 over 2 minus x greater than 0 or equal to 0. Because I want to know where the value of that expression inside is positive or equal to 0. So I could solve it graphically or algebraically. I'm going to solve it graphically because it's a little faster, I think. So I'm going to graph g of x equals just the input for that radical, not the whole original function. And I want to know where is the graph above or touching the x-axis. So I can see that there's a x-intercept at -3, a vertical asymptote at 2. They're each multiplicity 1. And I can also see that there's a vertical asymptote at horizontal asymptote at -1, because the numerator and the denominator are both degree 1. So I want the ratio of the leading coefficients, and the ratio of those coefficients is -1. I can also see that if I plug in x equals 0, I have 3 over 2, so 1.5. As I move to the right from there, I have to go up because there's no place to cross the x-axis. On the other side of that vertical asymptote, I have to be the other direction since it's multiplicity 1. And then moving to the left of this y-intercept, I know I'm going to cross that x-intercept because it's multiplicity 1, and then move toward my horizontal asymptote. So it looks like above or touching the x-axis would be this stretch right there. So the solution to this inequality is -3 to 2, including -3, but not including 2. So the domain of f is exactly that interval, because the inequality solution would be the inputs that work for that function f. So that's one place where we need to solve rational or polynomial inequalities, would be if we have a square root of a rational or a polynomial function, and we need its domain. Then let's take a look at solving one of these inequalities on our calculators. So if I want to figure out where x cubed minus 2x squared is less than or equal to 3x, I have really two options, or more, but two obvious options. I could graph y1 equals x cubed minus 2x squared, and y2 is 3x, and find the intervals of x values over which y1 is lower than y2, because we want x cubed minus 2x squared to be less than 3x or equal to. So below or touching. And then another option that will be easier to see would be to rearrange and just do a single function, and then find the intervals over which the graph of y1 is below or touching the y-axis. I said y-axis, but the x-axis. So either one is fine. Let's take a look at both. So option 1, I have one graph is x cubed minus 2x squared. And the other graph is 3x. I'll just do zoom standard. And I can see that those look like they cross 3 places. I'm going to change the window so that I don't see as much in the x values, maybe negative 5 to 5. It's a little bit easier to see. So I'll take a clip of that. Try again. So we want to figure out what are these 3 intersection points, and then we would want to figure out where is y1, which is the cubic or the degree 3 graph, below or touching y2. And it looks like we would want the intervals from that stretch and then this stretch. And on the other 2 intervals, the graph of y1 seems to be above the graph of y2. So let's find those intersection points. We would need to find 3 of them. Looks like one of them is at -1, -3. And one of them we can just see is 0, 0. So let's go find that last one. 3, 9. Right, so that looks like 0, 0, and if you plug in x equals 0 into both functions, you can see that they are the same at 0 there. So our 3 intersection points, -1, -3, 0, 0, 3, 9. We don't care about the y values, we just care about the x values. So the intervals of x values over which y1 is below or touching y2, looks like we'd have -infinity to -1, bracket, because at -1 they're the same, and then 0 to 3. Or the other option, if we graph just y1 equals x cubed minus 2x squared minus 3x then we are just looking at a single graph, and instead of comparing two graphs to each other, we're just comparing one graph to the x-axis, which is a little bit easier in my opinion. So let's take a picture of that. Paste it in. So here, again, we could go through and find the zeros, but we know from what we just did that's going to be -1, 0. That's 0, 0. And this is going to be 3, 0. So where the graph is below or touching the x-axis, again, that's just easier to see. That's that stretch and then this stretch. So our solution, -∞ to -1 together with 0 to 3. All right, and then the last one, using a graphing utility to solve a rational inequality. I would recommend doing the same thing we did when we were solving these algebraically. First, just get it into a single expression with a 0 on one side. So I would rearrange it, just like we saw with the polynomial inequality. It's easier to compare with 0 than to compare the two functions with each other. So I would do this. Put them together as 1. So this would be 5x plus 1 over x minus 3x plus 1 minus 3x minus 3 over x plus 1, x minus 3. So multiply the first term by x plus 1 over x plus 1, the second one by x minus 3 over x minus 3. Then you've got a common denominator, so we can do 5x plus 5 minus 3x plus 9 over x minus 3x plus 1 greater than 0. So that's, what, 2x plus 14 over x minus 3x plus 1 greater than 0. And then let's just graph that. And determine where is the graph above the x-axis. Remember, when you're entering rational functions, you want to be careful to get parentheses around the entire numerator. And the entire denominator. So you need x minus 3 in parentheses, and you need x plus 1 in parentheses, and then you want that whole group in parentheses as well. So you want to make sure you get it just like that. And let's just do z standard and see how it looks. So we can see that in the stretch between -1 and 3, where the vertical asymptotes are, the graph is below the x-axis. We can also see that once we pass 3, it looks like the graph is above the x-axis. We know from factoring this that there's an x-intercept at -7. So if I change my window a little bit to not see so much of the y values, we'll probably be able to see that a little better. We can see that the graph crosses out here. But it helps to think about, what we know about these graphs when we're looking at them on our calculator, because sometimes it's not as easy to see everything on the calculator. So we know that out here at -7, 0, there's an x-intercept, but that's the only one, right? And we know from what we just saw that the graph in this middle stretch is below the x-axis. So above or touching the, or sorry, just above the x-axis looks like this stretch. And this stretch. Let's see, -7 to -1, it looks like, where that vertical asymptote is, and then 3 to infinity. So as you can see, probably doing these rational inequalities by hand is easier than solving them on your graphing calculator, at least when the numbers are nice. It's not that nice to look at that picture on our graphing calculator, but to generate a quick graph by hand wouldn't be so bad. So hopefully that gives you an idea of what to do with these inequalities, and just to remember that it's more complicated than solving a linear inequality. The factors all work together, so we can't just treat it the same way we do a linear inequality. It's pretty complicated.